Okay, let's pick up with where we left off in lecture with these practice questions for the midterm coming up. Get you guys a little more clued in as to what's going on. This practice test in some forms, the conceptual questions are different than what will be on the final exam, but you should still be able to rationalize and get the correct answers, and even I feel that's important. So what do we have so far? Right. What we're looking at here is what we did in class. Uh, and we also did these in class. I did not circle the correct answer, it'd be B. We also did these in class. Circle B. And of course, the propagation of the error, propagation of significant figures to the calculation. We also did that here, right? The 5 significant figures divided by 4, meaning is 4. 6 significant figures and what's in the answer. We also talked about when we're doing addition with these scientific notation, where we have these powers. Find the answer, set all of them to the same power as the answer, and then do the math to see where your significant figure, or your the largest first unsignificant figure pops up. Okay. We talked about likelihood and probability a little bit, and just showing you that with a Gaussian, you have your next measurement has the 68.3% of falling between plus or minus 1 sigma. Well, we just say the probability is 0.63. It's just a factor of 100, so nothing new or interesting there. So this is where we left off. From a Gaussian curve, what is the probability that result from the population lies between mu and plus 1 sigma. So we're looking at this area here. We know that between plus and minus 1 sigma is 68%. So we're just looking for half of that, right, which would be 34%, or 0.342. And so that would be our probability of winding up between the mean and plus 1 sigma. The next question is basically the same. So we have a Gaussian curve again. We have our mu. We have our plus 1 sigma. We'll have a minus 1 sigma. And we want to know what is the probability of the population greater than plus 1 sigma. So what's your chances of falling into this range? Well, we already know that in between here is 68. So what would be, what falls outside of that? And that would be, of course, 100 minus 38, which would be 32%. So you have 32% of falling outside that area. But we don't want this left area, we just want the right, so it'd be half of that. So falling in this area over here is just going to be 16%, or 0.159. Okay. What would the what value would you calculate to determine the magnitude of the standard deviation relative to the mean? Okay, well, we just want to know, we want to compare a standard deviation to our mean, and what do we have that does that, right? Well, that's pretty simple, right? Standard deviation divided by our average times 100 equals our percent RSD, right? So that is our comparison, our standard deviation relative to our average. And of course, it also applies for the population statistics as well. So percent RSD. A sample of gold was measured 6 times and the falling masses were recorded. What is the value of the median? Well, what's the median, right? The median is the middle value. If you were to sort them all into high to low, what would be the middle value? If it's odd, you pick the middle value. If it's even, you pick the two values that are in the middle and you take the average. And we have an even number here, so we're going to have to pick the middle two, and we're going to take that average. The middle two would be 4.52 and 4.54 times 10 to the minus third, and we're just going to average those two together in order to get 4.53 times 10 to the third. You repeat a measurement 5 times and obtain the following results for the concentration of an unknown solution: 1.50, 1.48, 1.52, 1.51, 1.50. You're later told the actual concentration of the unknown solution is 1.34. Wow, we're off. Select the single treatment as true. The single statement that is true. Well, what do we have? Well, we have a series of measurements that are very well tightly clustered around 1.5, which means we have good precision, right? Our precision is good, okay? But we are way off the target, so our accuracy is poor, right? So let's look at our answers. Basically, the answers are broken down to two sections, right? We have the part on the left that talk about precision and accuracy on the left, and we have stuff on the right, which is what is the dominant error. So let's work on the left first, okay? Your results are precise and not accurate. Does that reflect what we have over here? Why, yes, it does. We are precise and not accurate. We're going to give that a check mark. The next one is your results are accurate, not precise. That is incorrect, right? We are not accurate at all. Once again, your accurates are precise and not accurate. Once again, check mark. And your results are accurate and not precise. Wrong. Let's look at the last one. Your results are equally precise and accurate. Okay, we already know that's not true, and the error is not significant. Boom. Okay, so we're down to two answers. And what's the difference? One, you want to know, is it dominated by systematic error or random error? Well, random error, right, would affect the precision, right? But it's not. Our systematic error affects our accuracy. So we are dominated by systematic error, right? So in that case, the answer would be A. An analogous question. Repeat 5 measurements and you obtain these results. 1.0, 1.23, 0.77, 1.17, 8.3. You're later told the actual concentration of the unknown solution is 1.01. Select a single statement that is true. Well, let's look at these values. Compared to the previous one, you should really never compare answers directly, but these are basically the same answer with just different flavor, right? Let's take these two measurements. Right, 1.23 and 0.77, you add those together. What's your value? 2. You divide by 2. The average of those two is 1. Right? What about the average of these two? Is 1. So basically, the average of our solution is going to be roughly 1.00 molar. Right? You're not required to have a calculator, so we're always going to give you simple math like this to you to look at. You should be able to get this by eye. Okay? And this value is very close to what the real value is. So our accuracy is good, right? However, our measurements are all over the place. If you were to look at this or number, or our average, which is 1, you'd see that we have like, wow, that's like over 20% error in a measurement. That means our precision is very poor, right? We're not reproducible. We're all over the place. But on average, we're hitting the right number. So let's dissect the answers. Our results are precise and not accurate. No, that is incorrect. That is opposite of what we want. Next one is our results are accurate, not precise. We're going to give it a check mark. Your results are precise, not accurate. Incorrect. Same as above again, so check mark. And then equally precise and accurate, we know that's wrong. So now we have to go back and what is dominating our system? Is it systematic or random error? Remember, we talked about previously systematic error. Systematic error affects our accuracy, and it's the random error that affects our precision. So in this case, our answer will be D. Okay, moving on. In the context of our discussion of error analysis, select all the statements that are false. Okay. Given systematic error affects the result in the same direction. Well, that is true. Okay? Systematic error will always move it in the same direction. Random errors can be eliminated completely with careful experimental design. No, we already know you can never get rid of random errors. That would be false. A mistake, like spilling or getting too pink in a titration, requires additional testing to determine whether the result can be rejected. Well, that's false, right? We already know it's bad. What is more testing going to tell us about that? If you spilled it, more testing isn't going to tell you that you spilled it. You know you spilled it. Okay, D. Systematic error reflects statistical fluctuations associated with a measurement. Remember, systematic errors are not statistical, right? You have a shorter measuring stick, right? Or something like that. It's systematic. Random errors reflect statistical fluctuations. So this would be false. It's straightforward to predict if an experiment will be dominated by systematic or random errors. Oh, you guys have done the experiments now. You know as well as I do, you never know what you're going to get. It's very hard to predict anything. So through all of these, select all the false statements would be B, C, D, and E. Okay. The sentence below refers to systematic error. Select all statements that are false. Personal errors such as human prejudice bias are a type of systematic error. Let's see. If I don't put my thermometer all the way into my solution, I won't get a good temperature reading. It'll always be a little bit cool. If I don't calibrate something correctly, it'll be off. If I don't read the burette level with the meniscus, I read it from the bottom up, I'll wind up getting a bigger number. So yeah, that's true. You and your biases and the way you run your experiments can be a type of systematic error. They can also be random error, but they just said a type. Does not all of them. Okay. The probability for systematic errors can be described with a Gaussian curve. Well, no. Once again, systematic errors aren't described with a Gaussian curve, right? Random errors are described with our Gaussian statistics. We've already talked about that. Instrument error, such as faulty calibration, are a type of systematic error. Yeah, we've talked about this. You calibrate it wrong, that number's off. You use a ruler of the wrong size or with an incorrect calibration. Yeah, totally going to be wrong. Flaws in the design of experiment are a type of systematic error. Totally true. You design your experiment around a device that is not calibrated correctly, you will have systematic error. Not a problem. Does it mean it's always that way? No, but usually flaws will cause both types of error. And then finally, systematic errors can be revealed or reduced by repetition. No, doesn't matter how many times you measure something with a short measuring stick, it'll always be wrong, right? So our false answers are B and E. Select all false statements about significant figures. The number 5.689 times 10 to the third has 3 significant figures. Oh, totally false. The number 201 has 3 significant figures. Totally true. The number 5,000 has 4 significant figures. Big false-a-rooney there. The number 0.02000 has 4 significant figures. Totally true. And the number 34 has 2 significant figures. Totally true. And we select the false ones, so A and C. Okay, moving on. Select the correct definition of significant figures. All the certain digits and no uncertain digits. Well, we know that's false. That is not correct, right? So when we talk about measuring the burette in class, right, we talk about all the certain ones, and then what is that last uncertain one too, right? Some of the class says 4, some class says 5, some say 6. It's all correct, but you also have that uncertain digit as well. B, all the certain digits that precede the decimal point. Well, that's going to be false because you're going to have sometimes numbers that are to the right of the decimal point. So that's kind of silly. All the certain digits reported on the instrument. That will be also going to be false, right? Just because the certain digits on an instrument, right, the last digit is uncertain. That's where the variety is. So an instrument always reports everything on whatever instrument is reports everything as a certain digit except for the last one. It is uncertain. D, all the certain digits that follow the decimal point, of course, we'll have ones to the left as well, so totally false. And then lastly, hopefully this is true, all the certain digits plus one uncertain digit. Totally true. That's exactly what we want. The answer is E. You measure the pH of your solution 4 times and get the identical result, pH equals 7.04 for each measurement. How should you report the error? Well, remember, this goes to rule 3, right? Is our standard deviation smaller than our instrument error? You know, does this make sense? Can we have a 0 error? Okay, A, report the error as the sample standard deviation, which is 0. We already know, totally false, not correct. B, report the error as undefined. No, we're not going to report the error as undefined. That is not what we do. We have never done that in class, and you shouldn't. C, report the error as the precision of the instrument. Yeah, we totally do that. Once you get too small, the best you can do is the instrument error or instrument precision, right? D, repeat the instrument until you get a larger sample standard deviation. Yeah, but it still may not be the level of the instrument, and you still may be close to 0, so no, that's not how we deal with it. And E, do not report error, totally false, so the answer would be C. Report the precision instrument. Rule 3, we've talked about it several times. Okay, the pH of the solution is 7.04. The corresponding concentration of protons is shown on your calculator as 1.0964782 times 10 to the 7th. Report this concentration with the correct number of sig figs. Well, remember, this is a pH. It's a logarithm. So what does that mean, right? The 7 is basically that number there, right? That's the same thing. We don't report that as being any part of a significant figure. This only has 2 significant figures, so this can only have 2 significant figures. So it would be 1 point, and that 9 rounds up to 1 times 10 to the 7th. So the answer would be C. Why is it important to report an experimental result with an associated standard deviation? Okay. The magnitude of the standard deviation reveals whether the experimental method was reproducible. Yeah, totally. If you have a nice small standard deviation next to your answer, you know that that thing was reproducible. It kept giving results within this small area. Or maybe it says, it was large, but it lets you know what that reproducibility is. Totally true. B, the standard deviation reveals how close the result is to the theoretical value. No, right? The standard deviation tells you how well you cluster around your average. If you have a large systematic error, you may not, or you don't even know what the target is. It's not going to tells you anything about your theoretical value in any way, shape, or form. C, the standard deviation helps predict the probable result if the experiment were repeated. Yeah, totally true, right? This gives you a probability of what your next measurement would be. Within 68%, your next measurement will fall in this range. Awesome. Okay, so this says, we'll skip ahead, A and C, of course, because we know B is wrong, so the answer is E. Okay. In 7L, we will calculate sample standard deviation based on 3 trials. Why do we care about the way we report a standard deviation? A, with only 3 trials, there's significant uncertainty in the sample and standard deviation. Yeah, totally, right? We talked about that in one slide. I said you don't need to memorize this equation, but we want to know the error in the error, right? The standard deviation of the standard deviation. And when n equals 3, we know that what? The error in our standard deviation was 50%, right? Huge. So when you have a small number of measurements, oh, I hate this pen. When you have a small number of measurements, you really don't even know your error that well. So yeah, with only 3 trials, it is bad. 2, B, error cannot be known with high precision given a limited number of trials. Also true, right? Once again, we're talking about the same thing we're talking about before here, where with limited trials, you don't know very well what your error is. Right? You have a calculated error, but there's still a lot of issues in it. C, the precision of the result should never be different from that of the standard deviation. Okay, this sounds true, but we got to be careful here, right? Quite often we can get standard deviations of what? 0 or a very small number. In that case, the precision of your standard deviation is way better what the instrument can do, right? So let's say you get a number 3.02, and this is the best the instrument can do, and then your standard deviation is that. Can you report this? And the answer is no, you can't do better than the machine. So never is, you have to be careful, right? The result should never be different than that of the standard deviation. Well, this is the standard deviation, right? But you can't do that, right? You have to go with what the instrument does. So this is totally false, right? So D, A, B, and C, no, and E, some of the above. Tricky question. Yes, tricky. Tricks these hobbits. Okay. The image of the bread was shown in class. How many significant figures should be reported for this reading? Well, let's take a look. It's between 30 and 31, so we know it's 30. It's between 30.2 and 30.3, so we know it's 0.2, and then we'll make a guess, right? It's about 0.5, so that would be 4. You attempt to measure the length of a piece of black metal using a ruler. How many significant figures should we report for this reading? Well, let's see. It's definitely bigger than 2, but not up to 3, so it would be 2. And then I don't know, 7? Right, that's the best you can do. You can't say 7.5, you can't do anything else, right? The first number that's not delineated is the decimal, right? The first number that's not delineated here was this, right? These the 0.2 and the 0.3 have lines, right? Here, the 2 and the 3 have lines, but the 0.7 doesn't. So the best we can do for this would be 2.7 or 2.8, and that would be 2 sig figs. You attempt to measure the length of a piece of black metal using the ruler below. How many figures should you have in this reading? Well, let's take a look. It's definitely bigger than 2. And this is the 0.9, the 0.8. It's definitely between 0.7 and 8. And it's, I don't know, halfway up there. So it's definitely between the two. So remember, we have delineations for the 8 and the 9, or the 7 and the 8, I should say in this case. So those are certain digits. The first uncertain one is the one that's not labeled, we guesstimate, and it's this one. So the answer would be 3. You perform a multi-step calculation with numerous inputs. Select a single statement that is true. Okay. After each step, retain all the digits as reported by the calculator or Excel, and round the data at the very end of the multi-step calculation. Totally true. But let's look at the rest just in case. There's like a A, B, and C. After each step, round the data according to the rules of significant figures, and use the rounded values as inputs for the next calculation. Yeah, that's totally bad, right? Total error you're going to start introducing as you run those numbers. C, convert the input values such that they have the same number of significant figures. Why would you want to do that? Just because they have different significant figures, they're different numbers, that doesn't make sense at all. Convert the input values so that they have the same number of decimal places. Why would you do that? That's crazy. This doesn't even make sense. And E, none of the above. The guidelines for multi-step calculations are unique to each calculation. No, that's not true. They're pretty much the same universally. So the answer for this will be A. Let's see. There is a very important rule for how results and its corresponding error should be reported. Select a single statement that is true. The error and result should have the same number of significant figures. No. Your error should have one significant figure unless it begins with a 1 or 2. In this case, that it'll have 2, but you have no idea. I mean, the average can have multiple. That's kind of silly. B, the error and result should have the same number of decimal places. Yeah, that's technically 2. If you have 1.23 plus or minus 0.02, you have 2 decimal places there. Not significant figures, decimal places, and 2 there. Yeah, that's true. C, the error and result should have the same number of significant figures and the same number of decimal places. Well, that is totally wrong. I mean, that's an and statement that combines A, so we already know that's false. The error should be reported with greater precision than the results. Oh, never true. Should be on the same order, right? And the error should be reported with less precision. Totally awful, right? So the answer, of course, for this will be B. Okay, so that is all of the questions we went through. I will upload this and good luck. Remember, there's office hours this Monday from 5 to 7 should you have questions on this stuff.